I want you to think about the last time you took an antibiotic. Maybe it was recently, maybe it was years ago. A course of tablets probably twice a day with food, finish the whole pack. Something that felt unremarkable, routine. The kind of thing you do and then forget. Now I want you to think about what that tablet was actually doing in your body. It was borrowing a weapon from a fungus. Specifically, it was deploying a chemical that a mold evolved millions of years ago to kill the bacteria competing with it for food. That chemical, refined, concentrated, synthesized in a pharmaceutical facility, was now running through your bloodstream, targeting bacteria by the same mechanism it evolved to use in the soil. You were, in the most literal sense, borrowing a weapon from a microscopic war that has been going on in the earth beneath our feet since long before humans existed. And here is the thing that I find humbling about this. People were using versions of this weapon thousands of years before anyone understood what it was or how it worked. Egyptian physicians were packing wounds with moldy bread. Anglo-Saxon healers were making garlic and onion preparations that modern scientists have tested against the most resistant bacteria we have and found to be effective. Honey has been used as a wound dressing continuously for over 4,000 years, and modern medicine has verified in molecular detail why it works. The survival cabinet, the collection of things humans have used to fight infection throughout history, did not begin in the 20th century laboratory. It began in a kitchen, in a garden, in the accumulated painstaking empirical observation of what works. And the laboratory, when it finally arrived, told us why it worked. Today we're going to go to both places, the kitchen and the laboratory, the ancient remedy and the modern drug. And we're going to meet some remarkable people along the way, including a woman in Illinois who went shopping for moldy fruit and changed the history of medicine, and a policeman whose story has been told wrong for 80 years. I'm Alexandra, welcome to the Hidden Life of Things, everyday history for anyone who's ever looked at something ordinary and wondered, how did this actually get here? To understand why penicillin changed everything, you need to feel what the world was like before. And the way to feel that is to think about small things, not plague, not cholera, not the great epidemic diseases that killed millions at a time. Small things, the ordinary injuries of ordinary life. A scratch, a cut from a kitchen knife, a tooth that ached and became infected, a child who grazed their knee and whose skin turned red around the wound and then redder still and then began to swell. A soldier with a wound that seemed clean at first and then a few days later unmistakably wasn't. Before antibiotics, those small things killed people. Not always, not even usually for most people with healthy immune systems and reasonably clean environments, but regularly, with a frequency that modern people find difficult to fully imagine because our baseline has shifted so completely. Sepsis, blood poisoning, the condition where bacteria enter the bloodstream and trigger a system-wide inflammatory response, killed healthy adults in days. Childbed fever killed women who had just given birth in maternity wards across Europe until a Hungarian physician named Ignaz Semmelweis worked out in the 1840s that doctors were transmitting it on their unwashed hands between patients, a discovery so threatening to medical dignity that the profession largely ignored it. And Semmelweis died in a mental institution, possibly from the very infection he had spent his career trying to prevent. Surgical infection killed patients who had survived the injury itself. A burst appendix, an infected wisdom tooth, pneumonia, any of these could be death sentences. The average life expectancy in England in 1900 was around 47 years. By 1950, after the widespread introduction of antibiotics and other public health measures, it had risen to around 69 years. This is over 20 years added to an average human life in half a century. No single technological development in human history has extended human life by as much as the control of bacterial infection. And the story of how we got there is not the clean, triumphant narrative that gets told in textbooks. It is messier, stranger, more distributed, and more dependent on people whose names most of us have never heard. Here is something that I think is one of the most important ideas in this whole episode. The people who used moldy bread on wounds, who packed garlic into infected cuts, who dressed burns with honey, those people were not primitive. They were not ignorant. They were doing something that is genuinely scientific in its method, even if not in its vocabulary. They were observing. They were testing. They were recording what worked and passing that knowledge on. In ancient Egypt, physicians were using moldy bread and copper salts as topical treatments for infected wounds from at least 1550 BCE. We know this from medical papyri. They didn't know what molds were. They had no concept of bacteria, but they had noticed carefully, repeatedly across generations of practice that wounds treated this way did better than wounds that weren't. The empirical observation was correct. The mechanism was invisible to them, but the outcome was real. Ancient Greek physicians made similar observations, so did physicians in ancient China, India, and across the Middle East. The pattern appears in too many independent traditions to be coincidence. It is the accumulated result of millennia of human beings paying careful attention to what happened when they tried different things on infected wounds. And then there is Bald's eye salve, a 1,000-year-old remedy from an Anglo-Saxon medical text called Bald's Leech Book, probably compiled in the 9th century CE. Contains a recipe for treating eye infections that involves garlic, liquor onion, wine, and ox bile, brewed together in a copper vessel and left to stand for 9 days before use. In 2015, a team of researchers at the University of Nottingham decided to test this recipe, not to demonstrate that it was useless, to genuinely test whether it worked. They made the preparation exactly as specified in the original text. They tested it against Staphylococcus aureus biofilms, including MRSA, the antibiotic-resistant superbug that is one of the most feared pathogens in modern hospitals. Bald's eye salve destroyed up to 90% of the MRSA bacteria in the biofilm. A 1,000-year-old recipe written by a physician who had no concept of bacteria, germs, or infection as we understand it, was more effective against one of the most dangerous drug-resistant bacteria we know of than many modern treatments. Because the Anglo-Saxon healer had been paying attention, had noticed what worked, and had written it down. The knowledge was there, hidden in plain sight in a manuscript that most people assumed was medieval superstition until someone bothered to actually test it. Let me explain garlic properly because I think most people know it's supposed to be healthy without quite understanding why, and the actual mechanism is much more interesting than the general idea. Garlic contains two things that live in separate compartments within the clove. One is a compound called allicin. The other is an enzyme called allinase. As long as the clove is intact, unbroken, undamaged, these two substances don't meet. They stay in their separate cellular compartments, inert, doing nothing. Now, why would a plant evolve this arrangement? Because garlic is not making medicine for us. It is making a defense system for itself. When a pest bites into a garlic clove, a soil insect, a fungus, a bacterium trying to eat the bulb, it ruptures those compartments. The allicin and the allinase meet. They react instantly, producing a third compound called allicin. Allicin is the chemical that gives crushed garlic its characteristic pungent smell, and it is, in the context of microbiology, a highly effective antimicrobial agent. It penetrates bacterial cell membranes and disrupts the enzymes that bacteria need to carry out essential metabolic processes. It kills them or prevents them from reproducing by essentially jamming their internal machinery. The important thing to understand is this: allicin is only produced when the garlic is damaged. An intact clove of garlic has no allicin in it. The moment you crush it, you trigger the reaction that creates it. This is why garlic must be crushed or chopped and used relatively quickly, because allicin is chemically unstable and breaks down within hours to have its antimicrobial effect. Cooking garlic destroys the allinase enzyme before it can do its job, which is why cooked garlic tastes different and lacks the antibiotic properties of raw garlic. The folk wisdom, eat raw garlic for its medicinal properties, is chemically accurate. The people who developed this knowledge over centuries of observation were correct, even without any understanding of allicin or enzymes or bacterial cell membranes. Honey is a more complicated story, and in some ways a more remarkable one. Honey is one of the very few foods that does not spoil. There are pots of honey found in Egyptian tombs over 3,000 years old that are still technically edible. Not appetizing by modern standards, perhaps, but not dangerous, not decomposed, still honey. The reason honey doesn't spoil is the reason it works as an antimicrobial agent, and it operates through several mechanisms simultaneously. The first is osmosis. Honey has an extraordinarily high sugar concentration and very low water content, typically below 20% water. When bacteria comes into contact with honey, the sugar concentration gradient pulls water out of the bacterial cells by osmosis. The bacteria essentially dehydrate. They shrivel, they die. The second mechanism is more elegant. Honey contains an enzyme called glucose oxidase produced by the bees that make it. Under normal conditions, in a sealed jar away from moisture, this enzyme is dormant. But when honey is applied to a wound and comes into contact with the slightly diluted, slightly more alkaline environment of body fluids, the enzyme activates. It begins to slowly convert the glucose in the honey into gluconic acid and hydrogen peroxide. Hydrogen peroxide is a disinfectant, the same substance in a much more concentrated form that you might use to clean a cut. In honey, it's produced in small, sustained amounts, enough to kill bacteria without being concentrated enough to damage healthy tissue. It is a slow-release, self-regulating antiseptic. Medical-grade honey, specifically Manuka honey from New Zealand, produced from the flowers of the Manuka tree, is now an approved wound dressing in hospitals across Europe and the United States. It is used on burns, on chronic wounds, on surgical sites that resist conventional treatment. The NHS uses it, the US military has used it in combat trauma care. 4,000 years of empirical observation validated by modern molecular biology, now sitting in a hospital wound care kit. That continuity is remarkable. Now we get to the story most people think they know. And as with most stories people think they know, the reality is more interesting than the version that gets told. In September 1928, Alexander Fleming returned to his laboratory in St. Mary's Hospital in London after a holiday. He had been studying Staphylococcus bacteria, a common cause of wound infections, and had left some petri dishes unsealed before he left. When he came back, one of the dishes had become contaminated with a mold, and around the mold there was a clear zone, halo of dead bacteria. The mold was producing something that was killing the bacteria around it. Fleming identified the mold as belonging to the Penicillium genus. He named the substance it was producing penicillin. He wrote a paper about it, and then, and this is the part the standard story usually glosses over, he essentially moved on. Fleming was a bacteriologist, not a chemist. He recognized what he had found, but he couldn't stabilize or purify the active compound in a form useful as a drug. The mold broth he produced had very limited potency. He tried it on some surface infections with limited success. He couldn't get it to work systematically, injected into the body where it would be needed to treat the infections that actually killed people. He concluded that it might have some limited topical use and largely set the problem aside. For nearly a decade, penicillin was essentially a laboratory curiosity. Fleming's 1929 paper was read, noted, and not followed up at any significant scale. The revival came in Oxford in 1939 when an Australian pathologist named Howard Florey and a German Jewish biochemist named Ernst Chain, who had fled to Britain to escape the Nazis, decided to investigate naturally occurring antimicrobial substances. They came across Fleming's paper. They began working on penicillin. What Florey and Chain did that Fleming had not was to bring the full resources of biochemistry to the problem. They worked out how to purify and concentrate penicillin from the mold broth. They tested it on mice infected with lethal doses of Streptococcus. The treated mice survived. The untreated mice died. The results were unambiguous. Now they needed to test it in a human. In February 1941, a 43-year-old Oxford policeman named Albert Alexander was dying in the Radcliffe Infirmary. He had developed a severe infection that had spread throughout his face and body. He had already lost one eye, his face was covered in abscesses, and infection had spread to his lungs. Every available treatment had been tried. He was deteriorating. Florey's team decided Alexander was a candidate for their experimental drug. On the 12th of February 1941, he was injected with penicillin. Within 24 hours, he began to improve. The fever dropped, the abscesses started to recede. His doctors described it as a miraculous recovery. A man who had been days from death was getting better. And then the penicillin ran out. Florey's team had so little of the drug that they had resorted to collecting Alexander's urine every day, cycling it back to the laboratory and re-extracting the penicillin his kidneys were excreting to reuse it. Even recycling it this way, they couldn't produce enough. The infection returned. Albert Alexander died on the 15th of March 1941. Now, here's the detail that most accounts of this story get wrong. Most tellings describe Alexander's original wound as a scratch from a rose bush in his garden. It is a good story, peaceful, a man gardening, a thorn, an infection from the most ordinary domestic accident imaginable. It is almost certainly not true. A 2010 interview with a medical historian named Eric Sidebottom and later a confirmation from Alexander's own daughter, Sheila, who was still alive and living in California, gave a different account. Albert Alexander was likely wounded during a German bombing raid, shrapnel from a bomb that hit his police station. His daughter confirmed this, noting that the Rosebush story was probably wartime propaganda designed to make the medical drama more palatable and less military sensitive. So the first human to be treated with penicillin was probably a man wounded in the Blitz, not a man pruning roses. The wound came from a bomb, not a thorn, and the doctors who treated him recycled his urine to extract enough of the drug to keep him alive for a few more weeks. History is messier than the versions that get told, and usually more interesting. Albert Alexander's death was not the end of the penicillin story. It was the proof of concept that made everything urgent. The problem was scale. Florey and Chain could produce enough penicillin for mice and barely enough for one human patient using bedpans and milk churns and bookshelves lined with shallow culture vessels. To produce enough to treat patients at any scale, let alone to supply a wartime army, they needed a completely different approach. In 1941, Florey traveled to the United States to seek help. He ended up at the USDA laboratory in Illinois, which had expertise in industrial fermentation. Specifically, they had been working with deep tank fermentation methods that could, in theory, produce penicillin at a completely different scale from the surface growth methods Florey had been using in Oxford. The team took on the challenge, and they immediately hit a fundamental problem. Fleming's original mold strain simply didn't produce enough penicillin. Even in optimal conditions, it was too low yielding to support mass production. So they began searching for better strains. They sent requests to laboratories around the world, collect mold samples, any mold samples, test them for penicillin yield. They tested hundreds of strains from across the globe. And the best one they found was in a fruit market in Illinois. Here is where the story gets slightly historically complicated, and I want to be honest about that. A woman named Mary Hunt, a bacteriologist at the laboratory who had been assigned the task of scouring local markets for interesting mold samples, and who became known as Mouldy Mary, is often credited with finding the cantaloupe. But some accounts, including one from Kenneth Raper, one of the lead researchers at the lab, suggest it may have been an anonymous housewife who simply handed a moldy cantaloupe to a guard at the laboratory entrance and walked away without leaving her name. Whether it was Mary Hunt or an unnamed woman in the fruit market, what is certain is this: a moldy cantaloupe from a market turned out to carry a strain of Penicillium rubens that produced initially around 200 times more penicillin than Fleming's original strain. After further enhancement through X-ray mutation and filtration, techniques applied to the mold itself to encourage more productive variants, the yield reached approximately 1,000 times Fleming's original. 1,000 times. That is what made mass production possible, not the chemistry, not the fermentation equipment, a moldy cantaloupe, either from a careful scientist who knew what she was looking for, or from a housewife who noticed something interesting and handed it on her way past. The mold strain from that cantaloupe, Penicillium rubens, is the strain still used to manufacture penicillin today. Every course of amoxicillin, every penicillin injection given in a hospital anywhere in the world is produced from the descendants of that one mold on that one cantaloupe, in that one market in Illinois in the summer of 1943. That is one of the most extraordinary single facts I have ever encountered in researching this podcast. By 1944, penicillin was being produced in sufficient quantities to supply Allied forces. It is estimated that penicillin saved over 12% of the soldiers who would otherwise have died from infected wounds in the Second World War. A number that, when translated into actual people, runs to hundreds of thousands of lives. After the war, the golden age of antibiotics began. New classes of antibiotics were discovered in rapid succession: streptomycin, chloramphenicol, tetracycline, and erythromycin. The pharmaceutical industry poured resources into antibiotic discovery. By the 1960s and 70s, there was a genuine and widespread belief in medicine that bacterial infection had been essentially conquered, that antibiotics were a permanent victory over nature. This belief led to practices that we now understand were catastrophic. Antibiotics were prescribed liberally for viral infections that they couldn't treat, for minor conditions that would have resolved without them, as a precaution when a precaution wasn't needed. In agriculture, antibiotics were fed to livestock, not to treat disease, but to promote growth, a practice that exposed billions of bacterial cells to low-level antibiotic concentrations for extended periods. And bacteria evolved. Bacteria reproduce in minutes, expose billions of them to a substance that kills most but not all, and you're running natural selection at extraordinary speed. The ones that survive have, by definition, some resistance. They reproduce. Their offspring inherit the resistance. Within relatively few generations, you have a population that the antibiotic cannot touch. This is not a complicated biological process. It is natural selection, operating exactly as Darwin described it, just very fast and with very high stakes. The result is what the World Health Organization now describes as one of the greatest threats to global health: antimicrobial resistance. Bacteria that resist multiple antibiotics simultaneously, MRSA, methicillin-resistant Staphylococcus aureus, which resists most of the antibiotics routinely used to treat Staphylococcus infections, NDM-producing bacteria, some of which resist almost everything we have. The pipeline of new antibiotics being developed by pharmaceutical companies has essentially dried up because the economics of antibiotic development are unfavorable compared to other drug categories. We're discovering almost no new antibiotics. The ones we have are becoming less effective, and the gap between those two facts is where the future problem lives. Here is where the story comes back to the kitchen, to the garden, to the 1,000-year-old recipe in an Anglo-Saxon medical text. Because the crisis of antibiotic resistance has done something unexpected. It has sent modern science back to look carefully at the things people knew before antibiotics existed. Not because those things are as powerful as synthetic antibiotics, they aren't, for deep systemic infections, but because they may contain mechanisms that modern drugs haven't explored. Because the bacteria haven't built resistance to allicin or hydrogen peroxide the way they've built resistance to penicillin. Because the combination of compounds in a natural preparation may work differently from a single purified molecule. Bald's eye salve, that Anglo-Saxon recipe of garlic, leek, wine, and ox bile, was tested against MRSA, not by nostalgic medievalists, but by microbiologists at the University of Nottingham who were genuinely looking for new approaches to resistant bacteria. It worked. The question is why, and whether the mechanism can be developed further. There is also an entirely different approach being investigated: bacteriophage therapy. Bacteriophages are viruses that infect and kill bacteria. They are the natural enemies of bacteria, evolved over millions of years to hunt specific bacterial strains. Phage therapy, using carefully selected bacteriophages to target specific infections, was explored before antibiotics became available, largely abandoned when antibiotics arrived, and is now being urgently revisited. The appeal is specific. Bacteriophages are extremely precise. Where a broad-spectrum antibiotic kills bacteria indiscriminately, including the beneficial bacteria of your gut microbiome, a bacteriophage targets only the specific strain it evolved to attack. And importantly, bacteriophages also evolve. They can develop new variants in response to resistant bacteria in a biological arms race that we can potentially guide and direct. Research partnerships between Western science and indigenous knowledge holders are also yielding results. Canadian researchers working with Indigenous elders have verified that prairie plants, including chokecherry and gumweed specifically, target the biofilms, the protective molecular shields that resistant bacteria use to hide from antibiotics. These are plants that have been used medicinally for generations for reasons that the users understood empirically without understanding molecularly. The pattern is consistent across all of this. People knew things worked before they knew why. Science is now telling us why, and in several cases, the things that worked are providing new starting points for solutions to problems that the era of synthetic antibiotics helped create. The kitchen and the laboratory are, in the end, working on the same problem, always were. So the next time you crush a clove of garlic and catch that sharp, distinctive smell, that's allicin, a chemical defense system that evolved millions of years ago, triggered by the rupture of a cell wall, doing exactly what it evolved to do. And someone, several thousand years ago, noticed that wounds treated with it did better and told the next person, and that person told the next person. The next time you reach for the honey jar, if it's good raw honey, you're reaching for something that contains a slow-release antiseptic system engineered by bees over billions of years of evolution, verified by modern biochemistry and used in hospitals right now. And the next time you take an antibiotic, if you take it correctly, finish the whole course, only when it's actually a bacterial infection, you are borrowing a weapon from a mole, a weapon that a woman called Mary Hunt, or possibly an anonymous housewife with a good eye for interesting fruit, helped make available to the world. From a cantaloupe in Illinois. The survival cabinet is not a historical thing. It is a living thing, in your kitchen, in your medicine cabinet, in laboratories trying to figure out what comes next. History isn't only in museums. Sometimes it's in the jar of honey at the back of your cupboard, and it has been working for 4,000 years. If this episode made you look at your kitchen differently, at the garlic and the honey and the small ordinary things that turn out to have extraordinary histories, that's exactly what I'm here for. The Hidden Life of Things is on Spotify, Apple Podcasts, and wherever you listen. A follow or a like is encouraged, and if someone in your life is interested in medicine, in history, in the long human fight against infection, send this to them. And here's your clue for next time. It is probably holding something together right now, somewhere within 5 meters of where you're sitting. You have used it without thinking, children use it at school, artists use it in studios, engineers use it in factories. Surgeons have used versions of it inside human bodies. It is over 200,000 years old. The oldest known example was made by Neanderthals, not Homo sapiens, Neanderthals, from birch bark tar, suggesting that the ability to make it predates our own species. It has been made from horse hooves, from fish bones, from tree sap, from insects, from milk, from natural rubber, from synthetic polymers invented in the 20th century. It has been used to repair broken pottery, to assemble musical instruments, to build aircraft, to stick stamps to letters, to hold dentures and plates, to attach soles to shoes, to seal wounds in surgery, and in one of the stranger chapters of its history, as a weapon. What is it? Stay curious. I'm Alexandra, and I'll talk to you next week.